Hi, in this video, we're going to talk about dimensionality reduction to improve data visualization. Okay, so what's the challenge? Sometimes we face data sets that have too many variables. So that's what we call the curse of dimensionality. It will vary the number of variables that authors will consider as high. Some will claim that after 10 variables, that's high dimensionality. But typically we can say that when you have like more than 50 variables, for sure that's like a high dimensionality, but in some cases you might have like thousands of variables. So what's the problem with that? So first, the interpretation and visualization is going to be difficult. At the same time, when you're trying to process that data, the resources that you need are going to be, you need more resources. Then of course the cost is going to increase. Then what is the solution? The dimensionality reduction is one of the possibilities here. There are different methods, different algorithms. In this video, we're going to talk about PCA, Principal Component Analysis. So the focus of dimensionality reduction here is to be able to visualize the data. But because let's say that we have 10 variables, it's going to be difficult to put them in only one plot. You will need like several plots as we have done in previous classes, using pair plots, facets, different approaches. But again, if you want to see all variables at the same time, it's going to be challenging, right? Because after 3D, after 3 dimensions or 3 variables, yeah, we cannot place them in the same plot unless some of them are categorical. And we have done that in the past. With categorical features, we can add different colors, different shapes for the points. So there are ways to put more than 3 variables, but you have like 10 or more variables. And if they are numerical variables, then it's going to be a challenge. All right. So what's the idea? The dimensionality reduction, the idea is to be able to bring our initial problem to 3 dimensions or 2 dimensions to be able to visualize them. Okay, so how dimensionality reduction works? So typically these algorithms will try to find redundant variables of the correlation among the different variables to be able to group those variables and reduce the number of variables that are needed. So it's gonna transform the correlated features into independent variables. That's the idea. In that way, we will be able to first we will need less resources to process our data, and then also we will be able to visualize in a lower dimension. This is very useful in our EDA, in the exploration data analysis. Instead of having like several plots, you can have one plot to get an idea of how your data set looks. Okay, so what is principal component analysis? So PCA is a linear statistical technique. Uh, this is like in regression problems, the most popular algorithm is linear regression. In classification problems, the most popular algorithm is logistic regression. Well, in dimensionality reduction, the most popular tool is PCA, principal component analysis. So it transforms high dimensional data into a lower dimension space. And the idea, and this is important, it's like when you do dimensionality reduction, you will lose some information. But the idea is to preserve most of it. So typically you will try to target to keep like 85% to 95% of the variance of your data. Now that's when you apply PCA in general. But when you're doing this to plot or visualize your information, sometimes you will lose more information. But again, this is just an approximation. It's just to see how it looks, and it's not your final analysis. All right, so what are the steps that you require in order to perform PCA? So the first one is really important. You need to standardize the data. That's what we call also to normalize the data. What happens is typically our variables in the data set, they have different mean, different standard deviation, they have different units. So if you leave them like that in some algorithms, it's a problem because you might give like higher weights to some variables. So to avoid that, you need to standardize. So remember the Z equation for that. So typically to standardize a variable, we use like the equation Z equal to each individual value. So this is per column. So xi, it's like the first value or I can be the second value, like, like you go over the whole column, minus the mean for that variable, the mean of that variable, divided by the standard deviation. All right, so typically most values will be between -3 and 3. So what is the interpretation of the z values? Well, you transform from x to z. X is the original variable, z is the standardized variable. So what you get is like the mean value of z is going to be equal to 0, and the variance and the standard deviation both are going to be equal to 1. Now, what is interpretation? Once you standardize, if for a specific value in that column z is equal to 0, that means that that value is equal to the mean. If the z value is, let's say, equal to 1, the interpretation is that that value is one standard deviation above the median, the mean value. If it's -1, or let's say -2, it means that it's two standard deviations below the mean value. So that's the interpretation of the z scores or z values. Okay, so once you have standardized your data, now every single variable or every single column in your data set will have the same mean and the same variance, mean equal to 0, variance equal to 1. Then the second step is to compute the covariance matrix. So the covariance matrix will capture the relationship between features. There is a key difference here between covariance and correlation. They are related, of course, but covariance is used to show you the direction of the relationship. So if it's positive, it means that both variables increase. If one increases, the other increases. If it's negative, then if one increases, the other decreases. That's what you get from the covariance. And from the correlation, you get both. You get direction, but you get also the magnitude. How strong is the relationship. You get both. All right. So with that covariance matrix, then we find the eigenvectors and the eigenvalues. The eigenvectors will show the direction of how strong is the relationship. So it shows the direction where you're going to maximize the variance that we represent. Remember that we want to capture most of the variance in our data. And the eigenvalues, they will capture the magnitude. So once we have the eigenvectors and eigenvalues, then we can measure like the importance of each component. So in step 4 is when we pick the principal components. So we select k components that will explain most of the variance. So the idea is like initially you have, let's say, 10, 30, 100 variables, let's say 30 variables. So we compute with the method 30 components. These components, these principal components, are not the same original variables. It's not like a subset, no. They are linear combinations of the original variables. So we get 30 pieces, principal components. We get 30, but not all of them. In general, they won't have the same importance. So the idea here is to pick the top k components from this 30 that will represent most of the variance. So again, in a general application, we will target to pick the k principal component that will capture at least 80%, right? Between 80 to 90, 95% of the variance. However, as I mentioned before, remember that we're using this in this specific case to visualize. So now we're limited because of that. Because when you're visualizing, we need 2 or 3 variables or 2 or 3 components. So that will be our limitation. But in general, you will target the number of components will be given by, and you will try to represent, like, as I said, 80 up to 90, 95% of the variance. Once you're done with this, then you can transform your data. Okay, so let's solve an example. Before we go to example, let me just define a principal component. What is like each principal component? So these are new variables. They are constructed, they are linear combinations of the initial variables. So let's say that we have 100 variables, x1, x2 up to x100. This is like my initial data set, right? We have 100 variables in that initial data set. Now, when we create components, The component will take the original variables. It will give some weights like coefficients, and it's a linear combination that will create our components. We can see that actually when we find a component, we will see the weight or the coefficient for on how each variable contributes to the estimation of the components. It's important because we need that information to be able to transform from the initial problem to the new problem with the component that we pick. All right, just to give you a little bit more of intuition before we go to the example, this is the idea of PCA. So here the dots, each point, this is our original data. So there are only two dimensions, x1 and x2. Actually, you don't need dimensionality reduction here because this is an easy problem, right? But it's just for academic purposes. So we have two dimensions here, x1 and x2, and you see the original points. Each point is an observation. So with the principal component, we will try to capture most of the variance, right, of these observations. So it makes sense that our first component will be this line, the green line, because if you notice that line is like it's going through most of the points, or the points that are not in the line are close to the line. So in that direction, we're capturing most of the variance. Now, an important feature of the components, of the principal component, is that they are independent. Because maybe someone will think, okay, if I create this one, I can also create another line here that also it's in the same direction, right? But the problem with this line or this vector is that it's not independent from the green one. Remember from linear algebra, if you have a vector, right? So how it's going to look another vector that is perfectly correlated to this one? They're going to be in parallel. So these two vectors are correlated because one, it's a multiple of the other. So they are perfectly, if they are in parallel, because they are perfectly correlated. Now, on the other hand, when they are independent when they are like perpendicular, right? Here, these two vectors are independent, right? So that's how PCA works. So the first principal component is this one because it's close to like most observations, explains most of the variability. But then the second component, it has to be independent. That's why it's perpendicular to the first one. So now these two can explain, of course, a high percentage of the data. So that's pretty much the idea on how PCA works, just to give you an intuition, because this is in two dimensions. But of course, the same thing will happen in a higher dimension. All right, now let's go to the example. Okay, so for this example, we will use Panda, Seaworm, NumPy, and from scikit-learn, we will use the data, and also the standard scalar. This is for the normalization, for the standardization, and also from scikit-learn, we will take the PCA algorithm. All right, so let's load our libraries. The dataset here, it's in scikit-learn. It's a breast cancer dataset. This is synthetic. It's a simulated information, so it's not real data. Okay, so in the breast cancer dataset, the idea is like to classify tumors. There are two types of tumors, benign and malignant tumors. And in addition, we have 30 variables that measure the geometry of the tumor. It gives you an idea of the radius, texture, perimeter, area, smoothness, compactness, and different attributes that can be measured. So there are 30 in total, right, for each observation or for each tumor. Okay, so typically this is a classification problem where you want to predict like if a new tumor is benign or malignant. That's the idea using these variables. However, when you're performing the EDA, it's important to see if there is if it's possible to see which variables are relevant to classify, to make the classification. You want to see the classes can be like classified correctly, even before going to creating the model. So that's possible if we can put everything in a single plot. Now the challenge here is that there are 30 variables, so how can we put 30 variables in a single plot? That's why we're going to use dimensionality reduction. To be more specific, we will use PCA for that. All right, so using our 30 variables, please notice that they have different units. The mean values, they have to be different because, for example, for the first one, if you look at the values, 17.99, this is the mean radius, 20.57, and if you compare these values with the mean perimeter, the perimeter is higher, the values, 122, so the mean value of this column is going to be higher. It's going to be higher for sure. Same thing with the standard deviation or the variance. So if you leave it like that, then it's possible that you're giving more importance to some of the variables. And that doesn't make sense because for us, at the moment, they are the same. All right, so that's why the first step is to standardize the data. That means to transform our data to find the z-scores, right? Values between -3 and 3, most of them. In some cases, we will see values that are outside that range. That's possible, especially when data is not normal, that will happen. But in general, that will suggest that those values are outliers or typical data. Okay, so using the standard scaler, we feed our data, so we transform it and we create our scale data. So please note that now the variables, like for each column, you have values, like with mean equal to 0 and standard deviation equal to 1. So this is our transformed data set, right? We haven't applied the PCA yet. This is just the initial transformation. Actually, this is very common also in clustering when you're doing k-means. This is one of the first steps. You need to transform your data, to standardize your data. All right, since there are 30 variables, so let's create 30 components initially. So here we're using PCA from scikit-learn. Then we input our data, our scale data, right, from the previous step, X scale, that's what we're having here. And now once we have our, we have applied principal component analysis, we want to see the importance of the variables, or not the variables, the components. So the way to see that is using this method, explains variance. So the explain variance will give you the percentage on how each principal component is contributing to explain the whole variance in your original data set. So the interpretation of this is a cumulative here. So for the first component, it's explaining 44.27% of the original data, almost half of the data. Now, if you add the second component, it's 63.2. So this one is the PC1 is the most important one here. PC2, the contribution, it's like 20%, right? Like 20 points. And now if you keep adding a principal components, of course, it's going to increase. If you add all of them, you get the 100% of the information. Now, if you are applying PCA just to reduce your data set and not, let's say that is not for visualization purposes, you can pick up to here, like in this area, in this range here. I mean, anything in this range is fine. Let's say that you want to keep only, this is 4, 5, 6 components or 6 dimensions instead of 30. That means that with the 6 components, you will be able to explain 88.7% of the variance of your original data. If you shift it to 7, you increase it by 1, then you will be able to explain 91% of the variance. Okay, this is if you use 7 components, right? It's a good deal. I mean, originally you were using 30 variables, but just by using 6 or 7 dimensions, you will be able to represent like most of the data. Now, the problem, as I mentioned earlier, not the problem, but the thing here is that this is for EDA purposes, and I wanna be able to visualize. That's why I'm gonna stick to 2 dimensions. I'm gonna add only component 1 and component 2. You gotta be aware that you're losing some information, right? We will be able to represent or see only like 63% of the variance, and that's fine. It's just to get an idea of how the data set looks, and if it's possible to classify the tumors, right, in our EDA. Okay, so once we have made a decision, I'm gonna stick to 2 dimensions, then we can again perform our PCA for 2 components, and once we have our components, then we transform the data. we transform the data. This is how we transform the, the normalized or standardized data. So what's happening here is that, remember that there were 30 variables. So PCA1 will take those 30 variables and it's going to create a value here. This is the transform value. And PCA2 will do the same. So it's going to take the original 30 variables. It's going to apply different weights to get the transform value. So this is applying the transformation. You can see how it looks, the weights or the coefficients. So for the model PCA2, we can see the components. So for each, if you see, we have here like a list here, this one. This is for the first component. So this is the contribution, the 0.2189 is the contribution of the first variable to that component. The contribution of the second variable is going to be 0.10, 0.22 of the third variable. And we have 30 variables, right? So these are the weights or contributions or the coefficients, because at the end, remember that the components are linear transformation or linear combinations of the original variables. So we use, or in this case, scikit-learn is using these coefficients to transform the original values. So this is for component 1, for the principal component 1, and this is for the principal component number 2. All right, so once we have our two components, which will help us to see like 63% of the variance of the original data, now we can create a plot. I'm going to create a scatter plot to see the two components, PC1 and PC2, right? And I'm going to add here the target, which is if the tumor is benign or malignant. This is this information is in the dataset. So let's see the plot, the result. So when you see this plot, you can see that most of the points are separated, right? I mean, you can kind of like classify the malignant from the benign tumors. 0 here is malignant tumor, 1 is benign tumor. So there is not like the problem here, the problem will be like if that is like complete, like they are overlapped, but that's not the case. It happens in some areas, but in general you can see that it will be possible to classify. It will be possible to classify. So it's really nice to see this because here we're visualizing like the 10 original variables, right? Even though we don't have the perfect picture, at least we get an idea in our EDA. And you know now that if you keep moving forward, for sure we will be able to classify these two tumors using the variables that we have, right? But that's thanks to the dimensionality reduction that is allowing us to visualize instead of the 30 dimensions, we're using only 2 dimensions to visualize most of our data. All right, so that's how important is dimensionality reduction. So just let's summarize the key ideas here. So PCA is a powerful tool to when we have a high number of variables and we want to be able to visualize them, and also when you want to decrease the resources that are required to process your data, especially if you're creating a model or finding a patterns. So you wanna reduce the dimensionality. Okay, it's important to know that PCA it's a linear, it finds linear relationships. If the relationships are non-linear, then PCA is not the tool. At the same time, PCA is only for numerical variables. So if they're categorical variables, PCA is not designed for that. There are some variations and there are different algorithms, but this one is not for categorical variables. Okay, so the dimensionality reduction is useful for visualization, but also for pattern recognition, prediction, and clustering. So it simplifies our original data for different purposes, as we have just mentioned. All right, I'm going to stop the video for now. I'll see you in our next session.